Hello everyone, my name is Christopher Thurgood and I'm going to present today HyperGS, Hyperspectral 3D Gaussian Splatting, and I'm going to walk you through how we've adapted the 3D Gaussian splatting problem for the hyperspectral imaging domain to enable high quality, efficient, null view synthesis at great speeds and robustness for the use of cameras. This is a project done by the University of Surrey with i3D Robotics with myself, Oscar Mendez, Erin Ling, John Story and Simon Hadfield. I think most people here are probably unfamiliar with hyperspectral cameras, so I thought I would provide a brief overview of them before we actually proceed. Hyperspectral cameras are quite different to conventional cameras, which provide us with an R, G, and B wavelength of the visible light spectrum. And the R, G, and B are quite sparse and give us quite a lackluster material perception of the world due to how poor the spectral representation is of the visible light spectrum. Hyperspectral cameras try to go the other way and are a lot more complicated. They attempt to provide a dense and wide coverage of not only the visible light spectrum, but also parts of the infrared spectrum. These cameras can therefore show us parts of the world that we just can't see naturally and uncover underlying details that can benefit society, from medical imaging, like how the blood flows across someone's skin, or how ripe a vegetable is in agriculture. And compared to multispectral, the actual amount of sampling is far more. So we're going for about hundreds of channels here. There are two problems with these cameras though. They tend to be incredibly expensive in terms of actual renting them out or buying them. And as the technology improves, we're seeing the price drop, but we still see that this is going to be a problem for many years to come. There's also a problem with how long it takes to capture a single image. So a snapshot style camera can be up to 10 or 30 seconds, and that's for the quickest capabilities they have right now. And depending on the camera itself and the lighting conditions around a hyperspectral camera, the number of seconds it takes to take a single image can be up to a minute or more. So we need to find ways to actually reduce this. So null view synthesis in recent years has found just tremendous advances, and we are seeing a huge focus on the RGB domain. But as I've said, RGB is quite limited in understanding the material properties of the scene and detecting subtle spectral differences compared to hyperspectral data, which can provide us more information about the world. Hyperspectral imaging captures this rich information, but it introduces a lot of complexities due to the high dimensionality and hardware-dependent camera sensitivity function. Our goal is to make hyperspectral neural view synthesis fast, practical, and accurate for all domains. Hyperspectral neural view synthesis has been done before. HS-NeRF was the first to sort of introduce this with their own two datasets that they released alongside the paper. HS-NeRF built their method on top of the NeRF-facto approach that a lot of people use and benchmark today. They allowed their model to learn sinusoidal encodings of the spectral domain, and in doing so, their final model was able to do super resolution in the spectral domain, meaning that they could take any of the channels and perceive the hyperspectral or visible light spectrum as a continuous function. Now, as great as this was, we found that it was slightly brittle, and the dependence on the number of images was quite high because of the underlying machine learning method underneath. So 3D Gaussian splatting was quite a natural approach to this. Furthermore, their benchmarking was slightly poor, only comparing against themselves and NeRF-facto. So being able to see what more modern methods like MIP-NeRF 360 or just the original NeRF, or how they all really compare, would actually be really beneficial to see what this domain actually looks like on the real landscape. Because they were able to provide us with two data sets, it means that we can actually have some real world 3D modeling of hyperspectral data, and we don't have to rely upon any synthetic data sets that we can provide ourselves, which don't quite represent the real world. So what are our aims and objectives with actually accomplishing this project? We want fast rendering, short training speeds, and efficiency on the GPU memory. And the reasons for this is because with hyperspectral imaging, we're dealing with a lot more data. And in doing so, we take up a lot more space in the GPU, and therefore inference speeds also become more problematic since the number of Gaussians that need to be rendered from each ray is increased, and therefore if the number of Gaussians is increased with the number of parameters it needs to optimize, training also increases. So you can imagine how adding all these things together can be quite difficult to have an overall greater impact on the actual accuracy of the system as well, as long as making this even possible. So here's the pipeline to HyperGS that I'm just going to go over in the methodology section here. And we begin by using the hyperspectral images with a convolutional pixel-wise autoencoder, which is one of our main contributions here. We get the volumetric renderer to create a latent hyperspectral image and decode it out pixel by pixel. And these are then used to train the full Gaussian splatting system after using the decoded image. And the loss from the decoded image is what propagates the Gaussians around the scene. We freeze this decoder so that the latent space is actually fully explored by itself without it changing at training time. We also provide a view-dependent MLP due to the use of this autoencoder that I'll explain in a minute. And we also update the densification and the global pruning method to the hyperspectral adaptive density function. So in order to get the hyperspectral 3D Gaussian splatting system to really recognize the camera sensitivity function and understand the sort of spectral shape of the images we want to create, we train a very fast and small autoencoder on the pixel-wise shapes of the hyperspectral images. And in doing so with some squeeze excitation blocks, we provide a pretty good way of telling the system the sort of spectral shape and spectral coherence across the whole of the reconstruction with the 3DGS system to explore. The systems here is frozen at training time, and we only use the encoder in the global pruning method that I'll discuss in a minute, and the decoder is used throughout training in order to get the decoded out hyperspectral images. This is pre-trained pretty quickly since it's running on hundreds and thousands of pixels in the images, so there's lots of data for it to train on. Because of the inclusion of our pixel-wise autoencoder, we basically had to remove the spherical coefficients of the system to the hyperspectral domain. And we had to do this for the baseline 3DGS system as well, because when you think about the number of spectral coefficients that would occur from the spherical harmonics, it would be the number of channels plus 1 squared. So 142 squared, it's a couple thousand, pixels, coefficients to really render out every time. So it's quite challenging to do so, and there might just not be a point of it with the solution that we provide here. So we actually try to add in view-dependent spectral lighting effects to the scene with the removal of the spherical harmonics using two separate MLPs. So in the hyperspectral domain, when spectral effects occur, like from lights in the surrounding area of where the picture was taken, only certain bands will actually be affected. So this becomes a bit more of a challenging problem, just raising all R, G, and B bands in the conventional 3D Gaussian splatting systems. And during training, we have a similar system to the Instant NGP nerf system, where the hash encoding MLP will take the positions of all the current 3D Gaussians in the system, and it will train how to volumetrically voxelize the whole scene. And in doing so, when the encoded outputs of these positions are then taken into a color prediction MLP, they then can gate the output with the original colors of the Gaussian's spectra. So this is all running in the latent space domain, but we also add a learnt alpha value from the MLP, and we found that this actually has a humongous effect on the actual performance of the system because of how complex hyperspectral images are and how difficult it is to get the correct spectrum, especially working inside of the latent spectral domain, because adding in high opacity Gaussians, we found that on certain channels they have huge effects, and so we really want the ability to remove the Gaussians and see the Gaussians when we need them, depending on where the hash encoding MLP is telling us. And in doing so, we get really good spatial-wise effects that stop blurring and floater artifacts that we usually see from the original Gaussian splatting system that we benchmarked from. As with any 3D Gaussian splatting system, structure from motion is actually quite critical, and this is just so that the model doesn't collapse and that the densification in the adaptive density function actually has something to densify from and doesn't have to prune too many as we can know from just using a random bunch of Gaussians at the initialization. So since hyperspectral data doesn't actually have a dedicated SFM pipeline, obviously without it getting too complicated, we actually have to do something a bit novel, where we first convert the hyperspectral images to grayscale by selecting the most high variance bands in the hyperspectral images. We then use Colmap with those to generate a grayscale structure from motion point cloud. And after we initialize our Gaussians, we have to back project all of the structure from motion points through the rays of the camera from the estimated camera settings from Colmap. And in doing so, we can basically get the same pixel for pixel value that the initial structure from motion point cloud points should have for the latent hyperspectral Gaussian signatures. So hyperspectral data is typically sparser and noisier, and latent spaces can just make this worse. So a simple threshold for Gaussian splitting can introduce a lot of visual artifacts, as we did with as we saw with our baseline 3D Gaussian splatting method. So our densification strategy addresses this by evaluating the gradients with respect to the training losses for multiple Gaussians from different views, right? And so we accumulate the loss from different perspectives, and then we densify based on the threshold of those, instead of what the original Gaussian splatting does, which uses a single Gaussian to see if it's explaining too much from a single perspective. And you can imagine in the hyperspectral domain that this is actually causing quite a large blur of the Gaussian over certain areas where there's a lot of detail, and areas with high detail or complex geometry are correctly split because of what the changes that we've made to our densification. One problem that we saw with this was that as the densification happens, we get a lot of floaters around the camera, and this was just purely because the certain Gaussians from different perspectives weren't being accounted for. So when they get thresholded, they get split as they are close to the camera. So in order to reduce the likelihood of splitting close to the camera, we actually scale by the depth from the camera. And so if the score exceeds a threshold and the Gaussians need to be cloned, they also need to be from a certain distance away from the camera position as well in order to split. And this allows us to adaptively refine the representation where the model needs more detail, and especially in spectrally complex or spatially discontinuous regions, while avoiding unnecessary duplication elsewhere in the scene. So even though we've now got this new densification method, we now have a lot more Gaussians doing a lot more in the scene, and we're losing out on that memory efficiency that I talked about in our motivation beforehand. So to maintain the efficiency and the number of Gaussians to be a lot lower and improve speed and all these other things, we introduce a global pruning method. So we take all the training images around the scene, and then we only perform a single forward pass, and we find the top K Gaussians, which not only are close to the ground truth spectrum or latent space spectrum that is correct given our the encoder part of our autoencoder. We also see how the transmittance and opacity of each Gaussian affects the scene, and we rank these top 10, and then we just remove all the others. And so what ends up happening is that this avoids over pruning, and we ensure that important spectral features are retained, but it also helps greater variation in each Gaussian to contribute to the scene. We found that this actually has some greater effects to the scene depending on where you actually have this global pruning method act in training. So we found that when you do this during the densification, you're able to remove a lot of outliers and worthless Gaussians that could potentially be cloned. And so what ends up happening is that you kind of strip away a lot of useless Gaussians without removing extreme amounts of detail that has been somewhat gained throughout the densification process. So if you do this, you then remove a bunch of Gaussians which are outliers, and you get more of a bare bones representation spatially and spectrally, which can then be correctly densified by the usual process of our densification function. And so with less Gaussians, it means our training speed is improved, and the overall ending model, even though this is done during densification, has less Gaussians overall because those outliers aren't being densified as well and contributing less to the scene. So does this work? Well, as you can see on screen, yes. Throughout all of our metrics that we added, so PSNR and SSIM for our spatial, and spectral angle mapping and root mean squared error for our spectral wise loss. And as you can see from the two data sets, that we've got some pretty unique variations in the results. So with our NeRF-based methods, you can see that in the base spec dataset where there's hundreds of images, it does quite well. It's able to generalize quite well to the scene. It gives more of a challenge to our HyperGS system, and it generally didn't actually do too bad. But what happened in the Surface Optics Pro dataset was the opposite. So we found that the 3DGS methods start to come out on top and the NeRF methods start to collapse. And this was just purely because the number of images is a lot less. And because the Surface Optics Pro is also a it has a lot less signal to noise ratio, the 3DGS methods actually starts to do really well. With the inclusion of noise in the spectral domain, 3DGS starts to fail, and even though you give it more images, it just can't quite handle it because it's trying to model the noise from every perspective, whereas the NeRF methods are able to overcome this and understand that if they generalize through the noise, then they get a pretty good result, whereas the 3D Gaussian splatting requires the smoothness. But HyperGS is able to overcome both the noise and the number of images in both scenarios. Here's some spatial wise and spectral sort of mean average error heat maps, as you can see, and you can see that there's actually a lot of detail that's recovered in both scenarios from the HyperGS system compared to the NeRF-based or the best NeRF-based methods, and even the 3D Gaussian splatting in both. Here are some pixel-wise losses, and you can see here that there's a general shape to the top and bottom rows of pixels that have been taken out of the system here. So you can see that, like, from the novel views at the same locations for these cameras, there's a general shape of it sort of be oversaturated and in the middle bits for the base spec, for instance, and the beginning parts of the spectrum being noisy. And even in the bottom Surface Optics Pro pixels, you can see that the camera sensitive function is also having a similar sort of representative function or shape of the spectrum as presented here. And all the systems are trying to also do the same. They're also trying to understand what the camera sensitivity function, and they're trying to model based on that anyway, and they're just modulating based on what the pixel is. So what's so interesting about all of this is that in the very bottom right image, this one, we can see that the HyperGS system is able to suddenly break out of the system, and it's able to understand that the camera sensitivity function isn't quite uniform for this area, and it's able to strategically keep that information correctly, and it's able to break out of the pattern that the others haven't quite understood how to get out of. So we just ablate here, and we can see that some of the biggest changes to our system that really made a big impact was the pixel-wise latent space autoencoder, a huge bump in PSNR, SSIM, SAM especially, where we can see this huge bump, and the number of primitives also changed just slightly. So it kind of suggests that this sort of smoothing of the noise with the latent space effect in the pixel-wise domain has actually really helped the system understand how and where to densify based on. The next biggest thing was the view-dependent MLP, being able to really understand the spectral-wise reflective effects upon the spectrum, and it's able to really keep up. We also had a customized loss function that helped the densification really understand the spectral-wise part of the scene, because we said it was based on the loss and gradients from multiple views. So a custom loss function, which included the spectral angle mapping of the produced images, also helped the densification understand where in the scene the actual spectrum itself was being poor, not just spatially. So the other ablation tables that we've got here is showing that when you change the brittleness of the latent space to a smaller value, the results get much worse, and this is understandable that the latent space isn't being as explored as it would be otherwise. And the second table here is just suggesting when it's best to actually densify and how many how to globally prune and when to prune in the system. And you can see that if you do it after densification, you get much worse results. But if you do it once or twice inside of the actual densification step, then suddenly we get some really good results. And the huge decrease from 1.3 million to 412 is just what with the results staying marginally close to what the original is with the densification is a testament to that. So where are we going now? So we're really want to explore some SLAM based version of this, being able to run in real time from a few images and see if we can get that working. We want to see if we can make some better data sets when our budget is increased, and we want to see if we can actually start doing some texture-based learning of the image slices that we used from the SFM and put that inside of the general formula for the volumetric renderer as well. So I think that HyperGS is great. It's been able to require less data. It's been robust across different cameras while providing some great results, and it's only slightly slower than 3DGS. It was recovering about 40 FPS, whereas the 3DGS was more like 60 or so. But with the 3DGS failing on a whole data set, I would suggest that HyperGS sort of overcomes the problems, and speed really isn't that much of an issue when we take into account the fact that the performance is just so much better in all scenarios. So thank you for listening, and I hope to see you at CVPR. Goodbye.